Solutions in Colloids, lecture number 13. So now we're going to start talking about not necessarily mixing one type of molecule with another and the effects of the intermolecular forces on there, but two different types to make mixtures. And we're going to start by talking about sort of classifying these two different types of mixtures that we're going to have here in terms of these solutions. The first one is this solution, which is a homogeneous mixture that exists in a single phase. So all the things come together in a homogeneous mixture in a single phase. Indistinguishable, so one thing is interacting with another because of these intermolecular forces and becoming indistinguishable from the other. The other type of mixture, remember, is the heterogeneous, and when we have this type of mixture in the liquid form primarily, or I guess one of the types of these types of mixture is called a colloid. This is a mixture that exists with two or more phases, and those phases are visibly distinct. So if you think about milk, we have that aqueous solution, the water, and then the milk fats that are solids in there. They're such a small thing that it looks cloudy, milky to us, but you can see those two distinct layers. Right? And typically in these colloid solutions we have either macromolecules, very big molecules, or clumps of really small molecules together. You think of this colloids, but also if you take salad dressing, for example, mix up the oil and the vinegar solution, you see there's these bubbles of the oil in this surrounding mixture of the water-soluble things. Again, the colloids are all heterogeneous mixtures, solutions are homogeneous. And we're going to spend most of our time in this chapter talking about these solutions. We introduced them last semester, but let's talk a little bit more in detail here in terms of these intermolecular forces. So remember, in a solution we have the solute and the solvent. The solute goes into the solvent. Solute is the one present in the smaller amount, the solvent in the larger amount, usually. And we can describe how much solute goes into the solvent using this term of solubility. It's the maximum amount of that substance that can go into a given quantity of substance, or solvent, at a given temperature. And we'll come back to this idea of temperature here in a minute, and its direct relationship to how these solutions are formed. And typically, we've mentioned this before, but typically the interactions that allow one molecule to be dissolved into another, or this solvation process to occur, is that we have similar intermolecular forces. So that the one molecule doesn't necessarily care if it's binding to another molecule of the same type or some other molecule, this solvent molecule, is next to it. The attractions are similar. So we can, in general, use the term like dissolves like. But the solvation process, or forming of solutions, is all based on these intermolecular forces that we've been talking about. If the intermolecular forces are similar, it's not going to matter to that molecule what it's surrounded with, either another one of itself or this other solvent molecule. When we talk about these solutions, though, we're really talking about breaking and reforming these intermolecular interactions. Right? So we can talk about the energy associated with that breaking or separation of molecules in very much the same way we've talked about breaking of bonds before, using this enthalpy idea. Right? So if we are breaking these molecules apart, not the molecules, but separating one molecule from another molecule, right, overcoming those intermolecular interactions, we have to add heat or energy to do that. So the breaking of these intermolecular interactions is going to require heat. So these are endothermic processes. So if we look at the solute molecules, separating those molecules is going to be an endothermic process. We're going to have to add heat. Same thing with the solvent. In order for the two to mix, we have to separate the solvent molecules. Again, overcome those intermolecular interactions. That's also going to be an endothermic process. But when they come together to form this solution, there's an interaction between the solute and the solvent. So there's going to be a intermolecular interaction there, which is going to give us a energy out. It's going to be a more favorable situation. So these processes, the mixture, the creation of the mixture, the solute-solvent interaction is going to be exothermic. So this process of mixing the two together is exothermic. So the solution is going to form if the exothermic, the ability for these two to come together, is outweighed by the interaction, the sort of endothermic energy we have to put together to break those individual types of molecules apart. And so if we look at this diagram before, if we put, say, sodium chloride in water and see what happens, we're going to see that we have to break apart this sodium ion and the chlorine ion. We have to break those two apart. Right? That's going to be attributed to this lattice energy that we've talked about before. But it's really that breaking of that positive charge with that minus charge, which we've said before is just an intermolecular interaction, a positive and a minus. Right? We also have to break the water molecules apart because the water molecules are sort of held together by this hydrogen bonding. So we have to break those, separate those two water molecules to allow one of these ions to come between. Right? So we're going to separate those. Both of those are going to be the solute and solvent. This delta H of those should be endothermic. But there's going to be this interaction between this sodium, the positive sodium, and the hydrogen bonding with a water molecule, the dipole. That's going to be a positive interaction. So it's going to be an exothermic process. So in that case, we should see a net overall delta H for an exothermic process. We can also see here we have an endothermic process that those two combined is going to be less than the thing formed. So I guess both are possible. One is more favored, though, than the other. When we talk about these aqueous solutions, we're talking about this, or the solvation. So the molecules themselves are separating those intermolecular forces of the solute. Right? That's the solvation process. With water, we call that hydration. So the water is forming sort of a hydrate around this solute. And this, so we have the delta H of hydration here instead of the delta H of mixture. Same basic process. Hydration for an ion is always exothermic because of the very strong ion-dipole interactions. So when we put things in an ion in water, because they're so much alike and there's a very strong attraction between the plus and the minus, we can get always an exothermic reaction. But that's not... Let's talk a little bit more about these delta H of hydrations. The delta H of hydration really depends, like all those, on the ability for that ion to interact with that dipole, right? That polar molecule. And as all times we've talked about these charge interactions, the two things that are going to have an effect are the magnitude of the charge of the ion, as well as the distance between those. Right? So we can say that sort of is the charge density. The smaller that ion is, with a higher charge, we're going to get a higher charge density. We get a higher charge, so the more positive that charge becomes, the smaller that ion is, which means it's going to be more strongly attracted to the H, that dipole of water. Right? Stronger attraction. So as this charge density increases, we're going to get a stronger interaction. So in both of these cases, the charge density as well as the delta H of hydration are going to decrease as we go down, so as they get bigger. They're also going to increase across the period as, again, those, remember if we talk about our periodic trends, as we go towards the noble gases, those molecules, or atoms, tend to get smaller, so their resulting ions should be smaller as well. And so we're going to get an increase in that charge density, and therefore the delta H of hydration. Right? But we can still do these same calculations as we had before. We're just now instead of breaking, like we talked about in the previous chapter when we're doing bond energies, we're just not really breaking bonds. We're breaking these associations and these intermolecular forces apart. It's the same general process. So the other thermodynamic variable we usually talk about is this entropy. Right? The entropy is the measure of disorder, remember. So as we form this mixture, we're going to get a increase in entropy. Remember, gases being the most disorder are going to have the highest entropy generally. Solutions are always going to be higher in entropy because there's more disorder in this mixture than in the pure solute or solvent. So every time we form these solutions, we get an increase in entropy, which is going to be favored both physically and in these chemical processes. So we see that when we're dissolving ionic things in water, we get both a thermodynamic variable. This delta H of hydration is going to be exothermic, which typically will mean the whole process is going to be exothermic. But also we have this increase in entropy, so we're sort of driving it towards this spontaneity. We can also talk about this process of equilibrium. Remember that equilibrium is a process where both directions of the reaction are possible and they're happening at a similar rate. So we can have this. When we talk about the solubility, we're really talking about is how much we can dissolve, or where we get an equilibrium between the soluble, the dissolved portion, and the insoluble. And that gives us two sort of different states. We can have at the saturation point, that's going to be called a saturated solution, where those two are in equilibrium. Right? The amount of, it's just as likely for a molecule to be in the solution as be outside of the solution. Right? If we're below that point, we are at the unsaturated solution. So there's a desire for those to be, there's a sort of a drive to go into solution. Right? We can actually, in theory, go beyond that, where we call a supersaturated solution, where there's more likelihood that that molecule wants to be in the undissolved state. Right? And what we're typically looking at here is this idea that the intermolecular interactions between the two is what's important, right? Which is going to depend on the types of molecules, but also the temperature. So the solubility then, as we showed earlier, is going to be dependent on the temperature, because the strength of those intermolecular actions versus the kinetic energy of the molecule is directly proportional to temperature. So we see that there is a temperature effect. And typically for solids, they become more soluble at higher temperatures because the kinetic energy of those molecules increases, which means that the strength of the amount of energy it takes to break either the solute-solute intermolecular interaction or the solvent-solvent intermolecular interaction becomes less. Right? This delta H of either solute or solvent decreases, which makes it more possible that those are going to separate and interact with the solvent. Gases, on the other hand, as temperature increases, they're more likely to, the kinetic energies allowing them to move faster and farther, they're going to be less likely to hang out within this solution. Right? So they're going to be more free to break out. The vapor phase is going to increase, if you will. Vapor pressure, excuse me. So gases typically become less soluble as the temperature increases, just because they have more desire to break through this liquid gas interface. Right? But there is this effect of pressure. Right? As the pressure increases on a gas, it's beginning to become more soluble. And we can think about that in this way. If we look at here, that if we increase the pressure, there's a driving force that's pushing gas molecules into the solution. Right? So that is causing those gas molecules to have less space and essentially forcing them into the solution, which is going to increase their solubility. We can define the solubility of these gases using Henry's law. So the solubility of a gas is directly proportional to the partial pressure of that gas above the solution through this. So S of the gas is equal to Henry's law constant KH times the partial pressure of that gas above the solution. All right, so we can do those calculations fairly simply. So remember, these solutions are just looking at the interactions, the intermolecular interactions between the solute and the solvent. Once we make those solutions, we can then need to relate how much, units to indicate how much of that solute is in that solution or in comparison to the solvent. And this gives us an idea of these concentration units. You've been exposed to these before. Let's just review them. We'll spend some time working between them in class. But the most common is this molarity, capital M, which is the moles of the solute per liter of the entire solution, as opposed to molality, little m, which is the moles of solute per kilogram of solvent. Right, notice those two are slightly different. The molarity is the entire solution. The molality is only the mass in kilograms of the solvent. Right? And then we have these sort of the percent by mass, or ratio of masses, parts by mass. So we can take the mass of the solute divided by the mass of the solution, or the total mass. If we multiply that by 100, we call that a percent mass percent. If we multiply it by 1,000,000, that's a parts per million. We can do the same thing in volume, where we take the volume of the solute versus the volume of the solution. Again, we can talk about part per million by volume. Or we can talk about this, as we did with the gases, this mole fraction, which is the fraction of the whole that is that solute. So the amount in moles of the solute divided by the total number of moles. Pretty sure you're familiar with all of these concentration units. We've discussed them, introduced you to them in the previous classes, but now we're going to begin working with them and sort of indicate how they interact in this solution. A couple of comments before we finish here about the converting between these concentration units. Again, we want to go to moles based on a mass. We need the molar mass. Right? Go from mass to moles, you need the molar mass. If you want to go from mass of 1 to a volume, mass to volume relationship is through the density. Right? So we'll see that these densities are going to play a role when we're converting between these mass units or concentration units. And as I said, the molality is for a given quantity, an amount of just the solvent, whereas the other ones are typically the entire solution. So in class, we'll be spending time working through these units and how they play a role in the rest of this discussion of solutions before next time we talk about their effect, the effect of these different intermolecular interactions these solutions have on the various properties we discussed earlier for the pure substances.